ability to actually observe them and resolve their structure is giving us great insight into the initial conditions of planet formation. It also tells us how planets form, especially if we can start to see signatures of that process starting within these structures. And it also feeds into our origins as well. And more, we're looking at the earlier phase. So the phase of the protostellar disk, when it's still accreting material, it still might be surrounded by an envelope, and it still might actually have outflows, because we're getting actually hints from ALMA that planet formation actually might begin quite early. Not just at this stage, the protoplanetary disk stage, but it also could be happening in this earlier stage as well. So those are the big questions on planet formation. But we have other big questions as well, which is related to the chemistry going on in these environments. And again, this comes down to our origins. So these structures that are built as stars form are really a unique astrochemical laboratory. And I'll give you a little introduction on what I mean by that. We are made of molecules. Our atmosphere is made of molecules, really, really important for not only creating a life-friendly planet, but also for the beginning of life itself. So by looking at the chemistry and molecules that are formed in these environments, we get to learn what is the origin or heritage of this planet and comet building material. Does the chemistry that happens earlier play a big role in setting the chemistry and composition of disks, which then feed planets? Okay. And that then gets us on to kind of the origins of life. Because as we know, our planet is the only place so far in the universe that we find that is host to life. So these are really interesting objects to study for all of those different reasons. But what do we mean? What is the anatomy of a planet-forming disk? What do they look like? So here's like an artist's impression, if you like. We imagine that we have a protostar that's just recently formed in the center, so it's quite luminous. It's blowing out lots of radiation, and it's surrounded by kind of this swirling structure of dust and gas. So these are generally, not always, but generally kind of axisymmetric structures. So very often we model them as two-dimensional objects. So here you're seeing a little cartoon that describes the anatomy of a planet-forming disk. So we have a star in the center, and as you see, we have kind of a midplane, which is kind of the ecliptic, if you like, the midplane. And then you see these disks have vertical extent. And that's because they're supported by hydrostatic equilibrium, much the same as our atmosphere is supported by hydrostatic equilibrium. And the star is the main source of heating in disks. So as you move away from the star, the disk will become colder. And as you move away from what we call the midplane towards the disk atmosphere, the disk becomes hotter, because that's the radiation from the central star can more easily penetrate up there and heat that atmosphere. So what are they composed of? So much like the interstellar medium, they're about 1% by mass of dust. And volatiles, by volatiles we mean gas, so things like hydrogen, carbon monoxide, water, etc., about 99% by mass. And the vast majority of those volatiles will be hydrogen and helium, with about 0.1% other heavy molecules. So you see here that I've kind of also split the disk a little bit. So as we move towards the outer cold midplane, we end up reaching temperatures below which ice can form. And the main component of the ice in protoplanetary disks will be water ice. That's kind of generally the most abundant ice that we have, that we also know from the study of comets in the solar system as well. But you'll see that, and I'll explain this a little bit more, as you move inwards towards a star, there will be again that temperature breached where those ices will sublimate, that will enrich the gas in water, for example, in the inner regions. But as you go up in the disk as well, towards the disk atmosphere, that ice is also lost, and we expect disk atmospheres to be mainly gas. So this kind of region where we go from ice to gas in the midplane is what we call the snow line. So hopefully you've heard of or met this concept of the snow line or ice line before. In the context of the solar system, the snow line or ice line discriminates where we have rocky planets in our solar system. So the four inner rocky planets, Mercury, Venus, Earth, and Mars, and the outer gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. I'm not going to talk too much about that today, but this is why the water snow line is so important, because if we can go and look for evidence of snow lines in other disks, we can start to see, do they have the same discrimination and kind of composition of the planets as our solar system does. So not only do protoplanetary disks have the water snow line, we also have other quite abundant molecules and disks as well that will have their snow lines at actually unique distances away from the star. And that's related to their volatility. So water ice is one of the least volatile. CO, as you see here, is a little bit more volatile, so its snow line lies farther out. And then one of the hypervolatiles, as we call them, carbon monoxide, lies farther out again. So as you can see, as you move out in the midplane, you expect the ice and then the gases composition to change. And here, water is in the gas phase, so is CO, so is CO2. If we're between the water and the CO2 snow lines, water has frozen out, but we still have CO2 and CO. And if you're between the CO2 and CO snow lines, then you've also lost CO2 to the ice as well. So we expect kind of elemental gradients in terms of the carbon oxygen budget in the gas and the ice as a function of distance away from the star. And this is very often used by the exoplanet community to try to infer formation locations of gas giant planets based on the kind of spectroscopy of their atmosphere. So again, really important for us to go and look for evidence of these snow lines in other disks. So if you're a disk around a sun-like star, then these snow lines would lie at these kind of typical distances. So the water snow line would be about 1, maybe 2 AU. CO2 snow line would be about 5 AU. The CO snow line will lie much farther out, so about 30, maybe farther, maybe 30 to 50 astronomical units. So you can see this is quite challenging because if you take a protoplanetary disk that's maybe 100 AU in diameter, you put it at 100 parsecs, you do the maths, you will see that's only one kind of arc second on the sky. So these are challenging objects to not only detect, but mainly to resolve. And I'm going to spend a lot of time today showing you what we've been able to do in terms of resolved observations of protoplanetary disks. But you can see here in this diagram, they also have these multiple snow surfaces. So not only do we expect kind of radial gradients in composition in the midplane, we also expect some kind of degree of vertical elemental variations as well. And unlike in the midplane, where temperature plays the main role in determining whether, for example, water is in the gas or the ice, in the atmosphere, it's really the radiation from the star that then sputters the ices away. So despite the outer region of the disk maybe being cold enough technically for ices to form, there's sufficient radiation to kind of remove those ices and enrich the gas in those elements. So one other complicating factor about disks, which is also very good for planet formation, is that the dust, even though it's 1% by mass, has a lot of physics going on and it evolves quite dramatically in the disk. So we have growth, so coagulation of smaller grains to form bigger grains. If we're in a region where fragmentation is important, so relative velocities are high, then we have bigger grains fragment to form smaller grains. If you have a dust grain in the outer disk atmosphere and it's sitting and it grows big enough, so typically that's of order about millimeter size, then it becomes decoupled from the gas, so it doesn't get dragged along by the gas anymore, and it feels the force due to gravity towards the midplane. This is what we call settling. So we expect large dust grains in protoplanetary disks to be highly settled towards the midplane and not distributed equally through the vertical extent. Another phenomenon of growth, especially in the outer disk, is that once your dust grains have grown big enough, then they want to move Keplerian velocity, but the gas feels its own gas pressure, so it's moving slightly slower. So it feels a headwind, this little dust grain, and if it feels a headwind, then it feels a drag force, which causes it to spiral inwards towards a star. And this is what we call drift. So we expect dust grains and protoplanetary disks to grow, to settle, and to drift. Okay. And this is really important for compressing the amount of material in the midplane to form planetesimals. This is what we need to form planets. And to concentrate material in a region of the disk where that process can also happen quickly before we lose dust to the star. And we see a lot of evidence of all of these effects in state-of-the-art observations of dust scattering and emission, as I will show you. So if we want to observe disks, what kind of are we really observing? Okay, so again, to continue with the little schematic, so we have radiation from the central star. That's controlling the heating, that's controlling the chemistry. So we end up, our chemical anatomy is that we have this frozen midplane, which is ices. We have a layer sitting above that, which is what we call the warm molecular layer. In the inner region of the disk, that would be hundreds of Kelvin. In the outer regions of the disk, that would be tens of Kelvin. And then because of the radiation, we have this thin layer in the disk atmosphere, which is atoms and ions. Okay. But the vast majority of stuff, for want of a better word, that we can see in the gas in a disk is going to be in this warm molecular layer. So when we point telescopes towards disks, we're really looking at this layer here. It's very hard to see the ices directly. We're really looking at emission from the molecules. So a lot of chemistry can happen in the disks, not only just from the UV and X-rays and the stellar wind. These disks are sitting in the interstellar medium, so they're also irradiated just by energetic particles that permeate galaxies, such as cosmic rays. And if you're nearby a stellar cluster, like if you're in Orion, then you may also have irradiation from nearby hot stars as well. So we can see that this is starting to get enormously complicated. It's not just that we have this two-dimensional structure. A lot of chemistry triggered by radiation can also happen in disks as well. So for example, here's where our snow lines would be lying. And if we want to observe, again, these molecules in disks and figure out what they're made out of, this is the way that we typically do it. So if we're very close to the star within 1 astronomical unit, we need to use near-infrared observations, but that's probing really hot material. It's thousands of Kelvin. Between about 1 and 10 AU, we can do that in the mid-infrared. So JWST would be our telescope of choice. And that's probing material hundreds of Kelvin. And you can see here we're still only seeing within about 10 astronomical units. The vast majority of disks are actually very cold, okay? So you see here, well beyond even the CO snow line, the outer regions of disks are between like 20, maybe 30 Kelvin. And we cannot observe them in the infrared. The molecules are not sufficiently excited into those vibrational states. So the only means that we have to observe the outer regions of disks is to use sub-millimeter observations, because that's perfect for probing material that's at tens of Kelvin. And that allows us to actually see the full extent of the disk all the way out to hundreds of AU, which is their kind of typical size. So we want to look at disks. In particular, I'm going to focus on what we can do in the sub-millimeter. So I'll tell you a little bit about ALMA and how we do that. So we want to measure their composition, but molecules aren't just interesting to determine their composition. And this is where astrochemistry, the field of astrochemistry, is really important. So we live in a molecular universe. We're made out of molecules. We're reliant on water, one of the key molecules for life. Our atmosphere is made out of molecules. Galaxies of the interstellar medium made out of molecules. Molecular clouds are required to have molecules in order to cool sufficiently to collapse to form stars. Those stars are surrounded by molecular disks. So we live in a molecular universe, and it's really important that we understand how those molecules are born, how they evolve, and then how they're delivered to planets. But those molecules are also really important diagnostics of just basic physics, right? So they give us an enormous amount of information if we can detect them about the environments that they're sitting in. So if we're thinking about doing molecular spectroscopy, and we can do that from the infrared right through to the microwave radio, that tells us what the gas mass and distribution is. Multiple line transitions can tell us the probe different excitations, can tell us the gas temperature. Using heavy molecules that are affected by collision rates can give us an idea of the gas density. Of course, we get the composition. If we spectrally resolve the lines, we can see how the gas is moving. So we can see gas in Keplerian rotation. If we measure line widths, we can get an idea of kind of the thermal and non-thermal contributions in that gas. So measurements of, for example, turbulence. And if we measure cations, so molecules that have or charge, so a very important one is HCO plus, I'll tell you a little bit about, then we can kind of back out using chemistry and chemical arguments the ionization fraction. And that's really important because how ionized the gas is will tell you how well coupled it is or affected by any present magnetic fields. And hopefully you all know magnetic fields are actually pretty important in star formation in particular. And just to give you a nice overview of like a beautiful spectrum. So I really like this spectrum taken with the Herschel Space Telescope of the Orion Nebula. Each of these lines is a detected transition in a molecule. And if we point to something like Orion, which is our nearest high mass star forming region, we see lots and lots of different molecules. We see water, we see sulfur dioxide, carbon monoxide, but we see big things as well, like I'll talk about a little bit later, things like dimethyl ether and methanol. So things that we might call complex molecules. So we've been studying disks and a lot of these molecular tracers for many decades now. And thanks to ALMA, there's actually been an explosion in the number of molecules that we've been able to detect. Okay. And remember, we need to do this in the submillimeter. We're probing cold gas, the outer regions of the disk. So it's pure rotational transitions in molecules that we're detecting. So this was a snapshot of detections in disks about 2021, so about 4, maybe 5 years ago now. So you can see here we see lots of small, what we call two-atom or diatomic molecules, so things like radicals like Cn or Cs or SO, sulfur monoxide. We see carbon monoxide as well. We also see three-atom molecules, so water. Here's some of these cations I told you about, so HCO plus and NH plus are two very important ones, but we see small organic molecules like C2H. Four atoms are starting to get a little bit more complex. It depends whether you're a biologist or an astronomer, what you define as complex. So we see acetylene, we see formaldehyde, we see ammonia. And if we go up in size, about 2021, we also started to see some bigger things as well, things that you might remember from your organic chemistry lab at school. So methanol is the simplest alcohol, and methyl cyanide is the simplest organic cyanide. So that was about 2021, but my colleagues and I have made much more progress since then. So we need to update this table. So we now can also see sulfur dioxide. We see these interesting organic radicals. We've done the first detection of nitrous oxide as well, which is very important in our atmosphere. And we're starting to see these much bigger things. So this is dimethyl ether, simplest ether. This is methyl formate. And then this is ethylene oxide. And actually, we've only ever detected ethylene oxide in a disk, which is very strange. Usually we see these molecules elsewhere. So not only is we can see the diverse molecules that we see in disks, but you can also see that we have lots and lots of information from all of these tracers to kind of dig around and get out the physics and structure of disks as well. So far we have 31 unique molecules. We have 18 rare isotopologues, so that's where we might have an element replaced by a heavier version. So for example, here you have H13CO plus, where the 12 carbon is replaced by carbon 13. So a huge amount of information, much more than we had when I started my PhD. It's almost overwhelming at this point. And as I'll show you, the observations are well ahead of the models at the moment. So our tool of choice is this beautiful array of telescopes here you see in this image. This is the Atacama Large Millimeter or Submillimeter Array, which is shortened to ALMA. And this is a wonderful instrument. This was like a big step change in our capabilities in millimeter interferometry from previous facilities. So ALMA has around 66 antenna. Most of the antenna are 12 meters. There's a small compact array of 7-meter antennas. And the longest baselines are 16 kilometers. So it gives us an enormous step change in collecting area because we have so many antenna. And those largest kilometers enable us to get down to actually about astronomical unit resolution in the nearest objects. So really, really powerful. It operates over an order of magnitude and frequency between about 30 gigahertz to 950 gigahertz. And that's perfect for probing the vast array of rotational transitions across a huge number of molecules. But the first thing that we've actually done with ALMA is look at the dust, because that's easier, because dust is broadband, okay? And we've done that actually at high resolution in probably of order about 100 objects now. And this is one of the kind of cornerstone programs which did that for the first time. So these are real observations, and what you're looking at is dust thermal emission from 20 protoplanetary disks. And all these protoplanetary disks are relatively near to us, so within 100 to 200 parsecs away. And what we saw with this large program, so this is the D-sharp large program, you see a huge array of different structures. We see rings, we see spirals, we see some disks are really tiny, like really compact, and some are really big. And we still don't understand that very well. And the reason that some of them look slightly different shapes is, of course, because they're inclined to the line of sight on the sky. So this one here is particularly face on, whereas on the top, in the middle, you see that's quite highly inclined to the line of sight. So this was amazing and really transformed our understanding of disks. So they're not those smooth structures like I showed you. They're not axisymmetric. The dust evolution is creating very interesting images in dust thermal emission. And if we take one example here, which is a star called HD 163296, so we don't see the star in the millimeter submillimeter. It's very, very faint. It's overwhelmed by the dust emission. So we have this inner disk. We have a big gap. We have a ring of dust with a little azimuthal asymmetry towards the south, another gap, and then another ring of dust. And the way that these have been interpreted, at least to date, although there's a little bit of debate about that, is that this must be evidence of planets forming in the disk. We don't see the planets directly, that's quite hard, but we do see gap clearing in the dust by those planets. So what the planets are doing is creating kind of gaps in the gas that is then trapping the dust in these rings. So whilst at the moment we cannot see very clearly, for example, in this disk, evidence of planets, this is kind of the favored explanation, if you like, of how we get these highly defined dust emission rings. So we can not only do this for disks that are kind of almost face on or only moderately inclined to the line of sight. There's been a lot of effort also looking at what we call edge-on disks. So disks that are edge-on to the line of sight, so that the disk is edge on. The idea being that we see the midplane directly. Okay. And this is another array of images. This is two types of imaging superimposed on each other. So the color map that you see in the background is scattered light. Okay, so that's done in the optical near infrared. So that's showing you the light from the star that's been scattered off the surface of the disk. So for tau 042021, you can see it looks a bit like a yo-yo. So you see the scattered light coming from the top and bottom sides of the disk. And then in the white contours, you see ALMA, okay? So where the white contours are concentrated, that's where the millimeter grains are emitting from. And you see very clearly in these images that confirmation of that process of growth and settling and drift. So the millimeter grains in these disks have grown, they've settled to the midplane, and they've drifted inwards. So you end up with this kind of concentration of your planet forming material very nicely in the midplane of the disk, which is where we want it. So that was a really neat complementary observations showcasing that process in action. So what about trying to see planets directly? So this is really, really hard. So it's much easier to detect planets when the disks have dispersed, and you can use coronagraphy, and you typically do that in the optical or infrared. To try to see planets actually forming within the protoplanetary disk itself is really, really hard because the disk is very bright and very often planets are very faint. But we do have one concrete example, and this is this disk here. This is a disk called PDS 70. And you see here, we don't see the star. We see some emission from the dust kind of sitting around the star. We have this big cavity, and then we have another ring of dust, okay? And this little point source almost here, which I've just ringed, that's the planet. And now we're not seeing the planet itself, we're seeing the circumplanetary disk that has formed around the planet. And that is really, really cool because one of the things that's when we don't really know is that if we look at our solar system, there's moons everywhere. The giant planets have hundreds of moons, probably. We can't count them all. Some of them are so small. The big ones we know for Jupiter and Saturn, of course. But one of the theories is that they possibly formed in a circumplanetary disk under the same physics as a circumstellar disk when those planets formed. And if you look at the mass of dust that we have in the CPD around PDS 70, it's about 3 Earth moons. So that's quite interesting. It looks like this planet, probably a gas giant planet, forming in PDS 70, has a circumplanetary disk that could then form moons. So that was a little bit of the dust, but what about the gas? Because the gas is actually what we have to observe if we want to learn something about the chemistry. So we've been doing that for a long time as well. So this is a really neat demonstration of snow lines. So here we have our nearest protoplanetary disk, TW Hydra. The green ring you see here is an interesting cation called N2H+. And it's actually telling us where the CO snow line is. So N2H+ forms between N2 and H3+, but is destroyed by CO. So where we see N2H+ lighting up means that CO must have frozen out on the dust grains. This is the CO snow line. So that's really cool. We've also done this a little bit more directly in another disk called IM-Loop, and this is another interesting cation, DCO+. And here you see the DCO+ emission is in 2 rings. So in between these 2 rings, we expect CO ice to be frozen out. So we have a double CO snow line in this disk. And again, this is due to astrochemistry. So we form H2D plus between HD and H3 plus. Then CO reacts with H2D plus to give us DCO plus. So where we see DCO plus, we must have CO in the gas phase. So this is one of the really neat early astrochemical results from ALMA. What about other molecules? So we're very interested in how much carbon and oxygen we have because that again is often used as diagnostic for exoplanet formation theories. So we do see small hydrocarbons, or we have seen in the past, small hydrocarbons. So again, this is TW Hydra, our closest protoplanetary disk. And this is another fairly close, well-studied disk, DM Tau in Taurus. And we're looking at C2H emission here. So this is a small carbon hydrocarbon molecule. And again, you see here that this emission is in rings, rings, rings everywhere, rings in the dust, rings in the gas. That seems to be what we're seeing. And what we think is happening here is that we're seeing a transition in the chemistry. So we see these hydrocarbon molecules, carbon-rich molecules, lighting up, becoming more abundant, where oxygen has been removed. So we think there must be very strong elemental gradients radially across these disks. So we've removed oxygen, probably through formation of ices in the outer disk, that leaves behind a carbon-rich gas where these molecules can form easily and then emit readily. So that's really neat. We're starting to see elemental gradients radially across the disk. So we see rings, rings everywhere. So for example, here is CS, again in TW Hydra, and this is CN, a quite high resolution, again in TW Hydra. These are 2 small radicals. And the reason that this emission is in rings is for actually different reasons. So this is what we call chemical rings. It also may be due to gas surface density perturbations. We need a higher density to excite the molecule to see it, or the UV radiation field from the star may be playing a role and how that's penetrating the disk. And that's been one of the reasons given for why the CN emission is in a ring in TW Hydra. So you see here, there's a huge complex interplay of lots of different things going on. We have dust evolution, we have a radiation, and we may have like radial perturbations in the structure, which could be leading to all of these chemical rings. So ALMA has also allowed, for the first time, us to see really big things, okay? So the first detection was actually methyl cyanide that was in quite a large disk around quite a warm star, so MWC 480. These are the detections, which were disk integrated spectra, so really, really difficult to do. And we're interested in cyanides because, again, origins of life. If we see cyanides in planet-forming regions around other disks, they're really important in the synthesis of amino acids. So we're interested in seeing these molecules. And looking at the ratio of the more complex to the more simple cyanides, we see between 5 and 20%, which is actually quite similar to what we see in comets in the solar system, which are kind of the preservation, the preserved remains of the icy material that form the planets in our solar system. So the next thing that we saw, which was work that I led back nearly 10 years ago now, was again TW Hydra, our famous protoplanetary disk. It's a solar-like star. Was the first detection of the simplest alcohol, methanol. And you see a little schematic of it here. Again, this was a disk integrated detection, so really, really difficult to do. The reason methanol is so important because it's really easily formed in interstellar space. And if you break apart methanol at different places, you make a lot of radicals which can recombine in different ways to actually form more complex molecules. So it's considered like a feedstock for complexity. And again, we did the calculation. We worked out how much methanol we had with respect to water. We discovered that was between 1 and 5%, which is really similar again to what we see in comets, maybe on the higher end actually of what we see in comets. So far I've kind of shown you the moderate resolution picture. So all of these observations have kind of the order of 0.5 arc seconds. So again, that's about 50 AU resolution for a disk that's 100 AU at 100 parsecs away. We see hints of this chemical substructure, and we also have a high enough sensitivity to see the first complex organic molecules in planet-forming disks. But what if we use ALMA in its full mode and we really push it and we really integrate for a long time, and we do that as at high resolution as we can? And this is a beautiful image of HL tau, which was the first long baseline image taken with ALMA. So what structure do we see, especially in the chemistry, if we go to that higher angular resolution? So this brings me to the MAPS large program. So this is a large program with ALMA, 130 hours, for which I was one of the co-PIs. And MAPS stands for Molecules with ALMA at Planet-Forming Scales. And our idea was to go look at 5 protoplanetary disks that are otherwise very well studied and resolve their chemistry at 0.1 arc seconds, so 10 AU scales. So the 5 disks that we had are these ones here. So we have IM loop. You can see the continuum, thermal continuum. This is the dust we're looking at here. See a nice spiral. GM Origai, which is rings. So does AS209, 163296 you've seen before, and then another Herbig star, MWC 480. Okay, and the scale bar here gives you 20 astronomical units. So we opted for these 5 objects. We wanted to go from younger, lower mass objects to older, higher mass objects to see if we saw any difference in their chemistry. So to give you an idea of the step change in resolution, so this is HCN in one of our disks at 0.5 arc second resolution. And when we use ALMA in its long baseline mode, so it's almost like looking at the disk with a microscope. This is actually what we see. So that blob of emission, which was unresolved, you see here the beam, suddenly becomes resolved into 2 very bright rings. And these data are so high signal to noise that we can put a stretch on the map and you start to see some other fainter substructure as well. There's actually a gap here in the outer disk, as well as seeing very clearly the edge of the outer disk as well. So these were the best resolved molecular line images of disks ever taken at this time. So we did that for the 5 disks, and we did that for 20 different molecules. So I don't have time today to go through all of them, but I'll show you kind of our postcard image. So here we have our 5 disks, and each of these columns is a particular molecular transition. So hopefully you will see that they're all very different. Sometimes the emission is very compact, sometimes it's more extended, sometimes it's in rings, sometimes it's smoother. No two disks look the same in any one molecular tracer, and no two molecular tracers looks the same in any one disk. This is really complex information that we have. So we have this huge diversity within disks and within the different chemical tracers. And we did the test where we said, if we see a chemical ring, do we also see a dust ring? And the answer was no. So it seems there's this really complex interplay of physics and chemistry that even now, 5 years later, we're still running models and still trying to understand. So the other thing we can try to do is look for planets in the gas, okay? And this has been successfully done for a handful of objects now. So this is not work that I was involved with. So what you're looking at here is a single channel of a channel map of molecular line emission and carbon monoxide, which is spatially and spectrally segregated because of the Keplerian rotation. So this is actually the gas disk you're looking at here. And then the rings that you see in the background are the dust thermal emission, okay? Now, if the disk is fully axisymmetric, we expect this bit of emission and the other side of the emission to be exactly the same. But you can see here in the white ring, we've actually got this strange little velocity kink that we think is because there's a planet in the midplane that's pulling material from the upper disk and perturbing its velocity relative to what it should be if it was purely Keplerian. So this is a really neat way of indirectly finding planets. So this brings me then just briefly to the ALMA large programs. This is not what I was involved with, but colleagues in Leeds and other collaborators that I have were. And this is one of the goals of ALMA. So they went and they selected 15 nearby disks and they looked at the disks at very high spectral, spatial, and high sensitivity resolution. Okay. And they're looking at carbon monoxide. And this is what they see. And again, these are really, really interesting observations. You see spirals here, more spirals. You see really, really clearly kind of the shape of the emission of the gas in the disk, and that's especially prevalent in the left-hand object in the middle row. We see gaps, we see rings, we see spirals, we see elevated emission surfaces. So again, really unique insight. But finding planets is really hard. So despite this very high sensitivity, high angular resolution, we don't have any smoking guns for the universal presence of embedded planets. And this is probably where we need next generation instruments to be pushed towards the capabilities to be able to do. And I'll say a little bit about that at the very end. So in this final little bit, I'll just talk about kind of pushing towards higher complexity organic molecules. So thinking about, can we form these large organic molecules important for prebiotic chemistry, and do they survive in these planet-forming regions? And we've been trying really hard. This is where I spend a lot of my time, is looking for these types of molecules with ALMA. So as part of MAPS, we actually have three what we call long chain hydrocarbons. So we have HC3N on the second row here, methyl cyanide again, CH3CN in the third row, and another small hydrocarbon, C3H2 in the bottom row. Okay, and on the top here you see again that continuum of our five sources. So hopefully your eyes will be drawn to the fact all this emission is really compact. It's not actually spread very fully across the disk. So we think a lot of the complex chemistry is actually driven by the ices that have been frozen on those large grains that have settled down and drifted inwards and compacted and compressed that material towards the inner region of the disk. And this is actually really useful for seeding life on planets. If we can take the molecules that we need or the elements that we need from the outside of the disk and bring them inwards toward to where the planets are forming, then that's really good, right? Because that then concentrates that material and maybe helps again to seed potentially habitable planets with the elements they need for life to begin. So we did another comparison with solar system comets as well. And so what you see here is for four of the disks where we have good detections. The orange region is the cometary value, and the blue lines with error bars are our data. And for these four disks, you see that the data, the observations overlap really well with the cometry values for these longer train hydrocarbons. So it looks like if we look at the composition in the planet forming region of these larger hydrocarbons around other disks, that composition matches really well with the spread of values we have in our solar system. That tells us that the same ingredients are formed everywhere and also roughly in kind of the same proportions, which is really interesting. So we're starting to find methanol in a lot more regions as well. So with one of my PhD students, Alice, we actually got the second ever detection of methanol in a disk. That was in this disk called 100546, which is very interesting because there's a couple of proposed protoplanets in it. You see here just this blob of emission in the central region that was detected. And the reason that this is interesting is because disks around her big stars, like HD 100546, are warm. And if you need to form methanol ice, you need CO to first freeze out on the surface of the grain. So we need to be beyond the CO snow line. And these disks don't have a CO snow line. At least we don't have evidence that they do currently. So we felt that this was very, very good evidence that material in disks is actually inherited from the interstellar medium. So the idea being that the disk forms with these ices already on the dust grains. Those icy dust grains grow, settle, drift inwards, where they breach the snow line for methanol, which is similar to the water one. They come up into the gas phase, and that's what we're detecting because it's really difficult to form the methanol in the disk. So we felt this was a very good evidence for what we call interstellar inheritance. This was the first hint that these warmer disks were chemically interesting. So we've gone back and we've actually looked at this other disk called IRS 48. It's a very weird disk. All of the millimeter dust is concentrated in this vortex here towards the south, but this is the most chemically rich disk we've ever discovered. You see here lots and lots of different molecules, including some of these really large ones. We have methanol, we have methyl formate, dimethyl ether, and again, the first detection of ethylene glycol. So the conditions within these disks around warm stars seem to be really advantageous, if you like, for these large complex molecules to form and to be seen in the gas phase. Although I would not want to say that these systems would be then host to potentially habitable stars because these are quite luminous stars. They're A-type stars. So here again is just an example spectrum of two of these objects. So we have IRS 48 in purple showing how dense the line spectra are. So really beautiful line spectra. And 100546, which seems to be more carbon rich. So we see more of these hydrocarbon molecules. So these Herbig disks, these warm disks, are really interesting chemically and are telling us a lot about how complex chemistry operates in that region. So just to finish, current ALMA has told us a huge amount about not only the dust structure, but also the gas structure and composition around protoplanetary disks. It can do that at high resolution, but only really with a very large investment in observing time, only really as part of a large program where we have hundreds of hours. So what about the future for ALMA? Well, it's currently undergoing a major upgrade. This is called the wideband sensitivity upgrade. So the back end, so basically, the bands that we observe in are all being upgraded. And the biggest upgrade there is also moving towards wideband receivers. So at the moment with ALMA, the correlator is incredibly flexible. You can set up tune the telescope, put in multiple observing windows, but the idea would be that you just observe the whole band in one shot, okay? And it will be able to do that at high enough spectral resolution to resolve lines. So we expect, whilst we're not getting any more collecting area, we're not increasing the resolution of the telescope, the efficiency of what ALMA can do now will increase by a factor of 2 to 4, depending on whether you're looking at lines or continuum. We can see a lot more in one shot than we can with the current collimator setup. So that's really exciting, and that's now started and will be coming in the next 4 or 5 years. What about the far future? Because we do have to think about the future of submillimeter interferometry. And this is where this concept coming in, ALMA 2040. So this is a collaboration, mainly European to start with, but it's a global collaboration. And what we are doing is coming up with a design concept for a future submillimeter interferometer. The idea would be we would increase the sensitivity compared to current facilities by a factor of 10, so a real step change, and also much longer baseline, so increasing the resolution by a factor of 3. Bigger efficiencies may also be able to be made through just better technology available in the 2040s. And I'm co-leader of the Planet Formation Working Group for ALMA 2040. The collaboration is fully open. We welcome everyone from around the world. You don't need to be a member of ESO. So if you would like to get involved, please contact me and I'll explain how to do that. And then to finish, the final thing I just want to point out is that I am also chair of a current running cost action called the Birth of Solar Systems, or Planets for short. We're currently in our third year of the action, and this is a network of about 400 researchers right across the world, all working together to answer some of those big questions about planet formation. Again, cost actions are completely open to join. People in Turkey can avail of all of the funding that we have because you are a member state. So if you're interested in joining our cost action, please also contact me because it'd be wonderful to have you on board. Okay, that's the advertisements done. So just to finish, so I did give you a kind of a tour de force snapshot of everything that we've done in the past 10 years. So what we're able to do now is high resolution observations that show us the composition in the planet forming regions. We can see this wealth of chemical substructure that we're trying to understand. The models are way behind the observations, so we have a lot of modeling and theory to do to try to explain that. We see when we compare with our solar system comets that the same molecules we see in the planet forming and comet forming regions around other disks are almost always in the same proportions as well. And we see these large complex organic molecules much more easily in the warmer disks than the cooler disks, but we have shown for the first time that they are there and can be abundant. And kind of the big message is that planets and comets do form in these chemically diverse environments. So when we're thinking about trying to interpret our exoplanet, spectroscopic detections of their atmospheres, measuring their elemental composition, we have to think really hard about what that means for the formation environment within the disk. And with that, I'll finish and thank you very much and happy to take any questions.
Thanks so much for amazing talk, Dr. Walsh. Does anyone have any question, guys? If not, I have two questions for you, Walsh. Do protoplanetary disks that share similar morphologies generally exhibit similar molecules abundance gradients?
So say that again, sorry.
Do protoplanetary disks that share similar morphologies generally exhibit similar molecular abundance gradients? I'm wondering.
So what we learned from MAPS, which is where we really resolved the molecular emission at 10 AU resolution, is that for some disks that have very prominent rings in the dust, we do see some mirroring of rings in the gas. So for example, for 163296, which has those 3 rings I showed you, we do see 2 rings in small hydrocarbons. So HCN and C2H, we see rings kind of mirroring or mimicking the dust. But if we look at another disk, we don't necessarily see that. So it seems that each disk is particularly unique. They're almost like snowflakes or fingerprints. And it's not always that we see the same type of chemical morphology in each one. The challenges behind that is that they're really hard to model because we have to put all the physics in, we have to do all the radiative transfer correctly, and then we have to do the chemistry. So we're a little behind in kind of getting that modeling pipeline through to kind of help us determine exactly why we sometimes see molecular rings and we sometimes don't, if that makes sense.
I see, thank you. And my second question is, estimating stellar age is still a challenging problem today, as you know. And I'm particularly curious about how this uncertainty affects planetary systems when we are trying to estimate stellar age. If system have, planets, it's pushing us, especially for the stellar age, and among stars known to host potentially habitable planets. What is the oldest age? I'm just wondering, if you looked at.
So these young stars that we're talking about here, I mean, you're an expert on this more than me. It's really hard to get a proper, robust age out because we cannot see directly the star because if we took a spectrum of the star, we're not just seeing the star, we're seeing all the material being accreted onto the star. So you get like a masking effect, which means that you cannot really use stellar evolution models to then determine what the age of the star is. So all of these stars are, they are no more than about 10 million years old, because that's the typical lifetime of the disk. After that, the disk disperses really quickly, and you end up kind of with a debris disk. So we have got good statistics that the disks that still have substantial dust and gas are likely less than 10 million years or less old. Now, whether they're 1 or 5 million years is really difficult. So very often the ages of these stars have big error bars, just because we can't get the spectra that we need to compare with the evolutionary models. In terms of what impact that has on our interpretation of these observations, it has a big impact because if you evolve a model for 1 million years, that's going to look very different to a disk that's been evolved for 5 million years because the chemical time scales are actually quite slow because the chemistry needs time to actually form all these molecules and for them to, be in the atmosphere and for us to see them. But it's true, I would say there's big uncertainties on the ages of the objects, but we can say more or less for certain they're no more than 10 million years old. Now, to the second part of your question quickly, for habitable planets, of course, it takes planets like the Earth much longer than that to grow, right? So gas giant planets need to form before the gas disk disperses. They have to form on timescales less than 10 million years. But terrestrial planets, we think, take more like hundreds of millions of years, right? Because we need two body collisions for them to grow, and that's just going to take time. So what role the disk then plays in setting the habitability of the terrestrial planets is more to do with delivery from icy bodies, okay? So the idea would be that we think that some of Earth's water and probably some of its organic material was delivered by impacts from comets and asteroids. We see that from isotopic signatures, so the amount of heavy water versus normal water, for example. But that had to have happened after the Earth formed, right? So the main thinking is that the comets in the outer solar system, kind of the leftovers, the proto-big Kuiper belt, because of the interactions between the outer giant planets, a lot of those were scattered inwards and hit the Earth and also hit the moon, but a lot of them were scattered outwards to form the Oort cloud. So the role of the disk would have been to set the composition of those planetesimals that then just frozen in and just sit there like as like a freezer, refrigerator in the outer solar system. The disk would have set that composition, but then how they get to the potentially habitable planets, probably some type of delivery would have needed to have happened. So there's a lot of steps there.
Yeah, yeah,
An
it's
annoying number of steps it's needed to actually form a habitable planet, which actually is another whole talk I have as well. But the disk is what will set the composition of everything that happens afterwards. There is a question in the chat.
yep.
So someone has asked regarding the velocity kinks in CO used to detect planets, what is the current lower mass limit for this technique? Can ALMA detect Neptune mass planets using these kinematic signatures? The current lower mass limit is definitely a few, if not 5 to 10 Jupiter masses. So we're not really reaching the sensitivity needed to see, for example, a Jupiter mass planet. For a Neptune mass planet, we're nowhere near that yet. So one of the science cases we have for ALMA 2040 is to do exactly this. So we've done some calculations to determine what sensitivity we need at what resolution to really distinguish the thermal emission coming from the planet from the thermal background emission coming from the background disk. Because we know planets form in disks, they must be there. It's just that we don't have the resolution or sensitivity to see them yet. But this is what we're hopefully going to do in our next generation interferometer. No problem.
So if you have no any question, I want to say thank you, Dr. Walsh, and I hope we can meet again in the next AS, in the Lausanne, right?
It is in Lausanne in Switzerland. Yes, it will be. Yeah. Great. Well, thank you very much for Khan again for the invitation. Very happy to chat to everyone today. Okay.
So have a great day.
You too. Take care.